Hello, welcome to Stoichiometry, which is probably a new word for you, and we're just about to learn what it means. You'll find that this refers to chapter 15 in your textbook, which we'll be basing it pretty much on. And so in this video we're going to look at what stoichiometry is, and then something called the mole ratio. What is stoichiometry? Well, stoichiometry is a term used by chemists for calculations based on chemical equations. So we've done a lot of chemical equations this year, and now we're actually going to do some calculations, some maths, even involving chemical equations. And stoichiometry is able to predict the relative amounts of substances involved in chemical reactions, and that ties in with what we've been just doing, which is using the mole concept, because stoichiometry relies pretty much on being able to use the mole concept. So, what does a balanced chemical equation tell us? Well, here's a word equation. One molecule of nitrogen gas reacts with 3 molecules of hydrogen gas to form 2 molecules of ammonia gas. Now that's the word equation. If we wrote it as a chemical equation, it would look like this. N2, because that's nitrogen gas, hydrogen gas, 3 of them, and ammonia is NH3, and we're told that it's 1, 3 and 2, and we don't need to write the 1 there because writing the chemical formula symbol is enough. Now, we've encountered that before, but now with stoichiometry we can start interpreting it a little bit more in detail. And so here, the coefficients, what we use to balance the equation, they tell us the relative number of moles, there's our mole concept, of reactants and products taking part in the reaction. And so we can say that 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. Okay, so using the coefficients, converting them to moles, tell us what's called the molar ratio of reactants and products. So this is where it ties into being so important, getting the correct formulas, being able to balance the equation, because that's the first 2 steps of stoichiometry, and then being able to use the mole concept to calculate and use the molar ratio. So all the stuff that we've been doing in chemistry in terms of those things all now tie into place, and it's crucial that you're able to do each of these steps. Now the mole ratio, so there's our equation. That's what it looked like if we drew it in space filling ball diagrams. And we're told that 1 mole of nitrogen reacts with 3 moles of hydrogen. 2 moles of nitrogen would therefore react with 6 moles of hydrogen. So we can use the ratio. As long as we maintain the ratio, we can use the mole concept. Excuse me. And half a mole of nitrogen would therefore, using the ratio 1 is to 3, half a mole reacts with 1.5 moles of hydrogen. So this is a ratio 1, 3, 2, and we can vary those numbers as long as we maintain that ratio. So what about what if we had 3 moles of hydrogen? That produces 2 moles of ammonia. Now if we had 1 mole of nitrogen gas that reacts with 3 moles of hydrogen, 2 moles produce 2 moles of nitrogen gas, ammonia gas. So we've done that one already. Now because we're talking moles can be represented by their molar mass, can't they? And so effectively this dot point here, where we have the ratio 1 mole to 3 moles to 2 moles, is the same as 28 grams of nitrogen gas, 6 grams of hydrogen gas can react together to produce 38 grams of ammonia gas, because that represents 2 moles. So if we worked out the molar mass of nitrogen gas, this would be 2 times it, and this is 3 times the molar mass of hydrogen gas, which is 2. And so we can see where using the mole concept can actually be translated into actual masses of substances. And if we wanted to be picky, we could talk about how many particles are reacting, remembering our conversion from masses or moles to number of particles using Avogadro's number and the formula on your formula sheet. Another example. Here we have hydrochloric acid reacts with magnesium metal to produce the salt, the ionic compound magnesium chloride, and hydrogen gas. We've done that with the POP test or various other reactions. We should be familiar with this because this is an acid metal reaction, and we've balanced it 2, 1, 1, 1. So that's our molar ratio, and it's written down here. So 2 moles reacts with 1 mole, 1 mole, and 1 mole, and we maintain that ratio. So if we had 2 moles of hydrochloric, 4 moles, 4 moles of hydrochloric, that would need 2 moles of magnesium, 2 moles, 2 moles. And if we did it, what's this? This is 2, so if we use 10, that's 5 times the ratio. So 5 times 1, 5, 5 times 5, 5 times 5. And half, 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 half. So we have to use the same multiplier or divider to maintain this ratio. 2 is to 1 is to 1 is to 1. Now that's, if we're looking, we can look at all the components, or we could just be interested in the hydrochloric and say the magnesium chloride. We don't necessarily have to worry about magnesium or chloride. It depends on the question and scenario. So we'll have a little thing that we can try. This is a little reacting quantities thing, which I'll put on the OneNote, and then I'll give you a copy of this table where we've got another reaction, and we just want to practice, or you can pause this and actually think about what the numbers would be here, and hopefully you would recognize. I'll just do the first line. The ratio is 2 is to 1 is to 2. So if we've got 1 mole of this, that must mean we have 2 moles of hydrogen gas, and we must have 2 moles of water. If we've got 4 moles of this, the ratio is 2 is to 1 is to 2. So 2 is to 1 is to 2 is the same as 4 is to 2 is to 4, and so on. But I'll print out a copy of that for class. And similarly, this one, a bit more complicated in that here the ratio is 2, 1, 1, 1, 1, and there's 5 things, but we've just got to practice making sure that we understand the mole ratio, because it's a fundamental thing in stoichiometry. What does the chemical reaction not tell us, which is an important thing as well? It doesn't convey anything about the rate of reaction, whether it's a rapid reaction or a slow reaction. You'd actually have to use some other data to calculate that. The equation does not tell us whether the reaction requires heat or gives off heat, so it doesn't tell us if it's endothermic or exothermic. It doesn't tell us if there's a temperature required for it to happen or a pressure required for it to happen. It doesn't give any details as to how the individual atoms or molecules are transformed from reactants to products, so it doesn't tell us about the electron transfer or anything like that. And so we just got to be mindful of that. It doesn't tell us everything, but it's the molar ratio and the balanced equation tells us lots. So let's do a sample using an equation to calculate moles of reactants used and products formed. So methanol, which has the formula CH3OH, is used as a fuel in racing cars. You can smell it if you ever go to the racetrack or the drags. The equation for the combustion is this. Now it's been nicely balanced for us, and the ratio is 2, 3, 2, 4, which is a bit more complicated than we've been doing previously, so it's a bit more challenging. And we're asked how many moles of oxygen are needed to react with 4 moles of methanol, and that will be relying on the molar ratio. And the next question is how many moles of water are formed when 1 mole of oxygen reacts completely with methanol. So we have to apply this ratio 2, 3, 2, 4. In the first one, we're given 4 moles of methanol. So we have a 4 here. Okay, and we're asked for how much oxygen is going to be used. So we want to maintain the ratio 2 is to 3. So 2 is to 3 as 4 is to, hopefully we recognise, 6. So 6 moles. Now how many moles of water, let's pick a different colour, are formed when 1 mole of oxygen reacts? So if we have 1 mole here, we want to know how many moles of water. So 3 is to 4 as 1 is to, and that's a little bit trickier. So this is, hopefully I'll get this right, 3 is to 4 as 4/3 is to 1. And let's just do that. They've probably written it in better words than me, so let's have a look at what they say. Okay, first off, we've got the first one, 2 moles reacts with 3, so we've got to maintain the ratio 2 is to 3, so therefore we need 6 moles. The next one is 3 moles of oxygen to produce 4 moles. So recognise that this is 3 plus 1, and 1 is a third of 3, and so that's where they get the extra third from. Okay, and we can do a little bit of maths in class if you need to figure that out. Hopefully you've done some ratios in maths already. So you can now do this question in the textbook, have a go at it, and this question number 2 as well out of chapter 15, and in the next video we're going to do what's called mass stoichiometry. Alright, see ya.